Hello, welcome to another lesson. In this lesson, we are building a network packet sniffer using Scapy. We are going to import and use Scapy, capture live network packets, analyze packet layers to extract information, and create a complete packet sniffer script. This is real network analysis at the packet level. Let's dive in. Before we proceed, ensure that you have your Visual Studio Code open. Now, this is the code for our package sniffer tool that we want to build. I'm going to add the link to the source code in the description. So just check the description. You're going to find the link to the source code there. And to be able to create it, the first thing you need to do is to create the file. This is the file here. And after that, you can copy the code and put it here. But the code is meant for practice. So I would advise that you understand the code first, try to write it on your own, and in case you made any mistakes, you can come back to the code to check the solution. So let me explain what the tool does. This packet sniffer captures network traffic flowing through network interface. It sees every packet such as HTTP requests, DNS queries, TCP connections, and everything. We are using Scapy, and that's because it is the most powerful packet manipulation library in Python. With Scapy, we can capture packets, decode their layers, extract information, and even craft custom packets. This is similar to what Wireshark does, but we are building it programmatically. And by the end of this lesson, you'll be able to understand how network sniffing works at the packet level. Now, if you look at the code, the first thing we are adding is our shebang. And after that, here is a doc string explaining what the tool is all about. And this is where the entire code starts from. So it starts from there. And if you scroll down, you are going to see the end of it here. But before you can run this code, you need to install Scapy first. But I wouldn't want that you install this on your machine directly. So the first thing I would suggest is that you create a virtual environment. So virtual environment is just like you are creating a container where everything you want to use for a particular tool resides. So we can create a container by using python-m, then we say venv, and we can call it sniffer-m, that is sniffer environment. Then we create it. And if you come here, you can see the virtual environment folder here. After you have done that, you want to now move into that environment. And to do that, you're going to run source sniffer, which is the name of the environment, sniffer env /bin/activate. So here we are activating the environment. That is, we are moving into the environment now. After activating, the next thing we want to do is to install our Scapy inside. So we are going to type pip install Scapy, and we're going to run it. And because I already have Scapy installed, it's saying the requirement already satisfied. But in case you don't have it installed, it's going to show you as it is installing. Now that we've installed that, let me now show you what the finished tool looks like in action. And after that, I will now walk you through the code base to explain how the code is structured. So to see what the tool looks like, we are going to type sudo python sniffer.py because our packet sniffing tool requires root or administrator privileges, and that's because it accesses the network interface at a low level. So that's why we are adding sudo. Now we can run this, and at the beginning here you can see a banner which is saying Python packet sniffer with Scapy network traffic analysis tool. Then after that, we are showing a warning, which is packet sniffing requires root privileges. Only sniff networks you own or have permission to monitor. That is the disclaimer. After that, we are presenting 4 options to the users. The first one is that you can sniff all packets. Second one, you can sniff HTTP traffic only. Third one, you can sniff DNS queries only. And the fourth one is you can exit. Now, let's pick one to sniff all packets. And the moment we do that, you can see press Ctrl C to stop. That is the command you will use to stop. Now you can see that it is sniffing packets already. And if you start scrolling down, you start seeing the results showing the packets that is being sniffed. You can see packet 15, packet 16, packet 17, packet 18, packet 19, and it continues like that. In case you are not familiar with what packet sniffing is all about, packet sniffing is the process of capturing, logging, and analyzing data packets as they traverse a network. They are acting as a wiretap for digital traffic. And as I said earlier, what it does is that it collects packets from a network interface, decode raw data, and then display its content, including headers and payloads. And those are the things we are seeing here. You can see that at this point, we are sniffing all packets. We are not picking a particular packet to sniff. If you keep scrolling down, you keep seeing all the packets that are being sniffed. This is packet 46, and it continues like that. So to stop this, I'll use Ctrl C to stop it, and now you can see that I'm back to the options. The second option is sniff HTTP traffic only, so I can select 2 to sniff HTTP traffic only. So after I've run that, I can come to my browser to open a few things. I can just try victorakionde.com, and I can move around to see if any packets will be captured. Let's go back to see that. You can see that some packets have been captured already. You can see that here. Also, I can come to my terminal here and I can type curl and http google.com. Then I can run it. So if I should come to my tool again, I should be seeing some results coming from that. And you can see the time, you can see the source IP, you can see the destination IP at the same time. And here, if you look at this, you can see 200 OK, you can see the content length, you can see via Google, and this is the date I recorded the video. So we can see that this is sniffing our HTTP packet as well. So let's use Ctrl C again to close that. And what if we want to sniff just DNS queries? We can just type 3, we hit enter, and here you can see starting DNS packet capture, press Ctrl C to stop, and after some time it will start sniffing DNS queries as well. So we can just close this, and if we want to exit it, we'll type 4, and then we exit, and now you can see exiting packet sniffer. So that is how our packet sniffer works. So let me now walk you through what the code looks like and how it works. After the docstring and the shebang here, at this point, we are importing all the packages or libraries that we need. So if you look at the first line here, we are importing everything from scapy.all using the asterisk, and this gives us access to all scapy functions and packet types. In production code, you can import specific items, but for learning, this is convenient. Also, we are importing sys for clean program exit, and we also imported datetime for timestamps. Then after that, if you come to the global packet counter section here, you can see that we are setting our packet count to be 0, and this tracks how many packets we've captured. We use a global variable because we are defining the variable outside any function, and we are doing that because our packet callback function needs to increment it. We are going to see the function later on. Also, this is simpler than passing states around. Then after that, we are creating a function here, which is the packet callback function. And this is the core of our sniffer because every time scapy captures a packet, it calls this function. Now let me break down this function. Here we are declaring a global variable, which is the packet count, and we are doing that so that we can modify the global variable and not create a local one. After that, we are incrementing the counter, and then we are printing a packet header with the packet number and timestamp. The timestamp includes milliseconds for precisions, and the /-3 here removes the last 3 digits to show milliseconds instead of microseconds. After that, we are now checking if the packet has an IP layer because not all packets do. Some are just Ethernet frames or ARP packets. So the has layer method we are using here returns true if the specified layer exists. If there is an IP layer, we extract information, and scapy makes this beautiful. We also access the IP layer with the packet in scare braces IP, then we get the source with the .src here, and destination with the .dst here. The protocol field here is a number. 6 means TCP, 17 means UDP, and 1 means ICMP. We are going to decode this later. Now let's move into the TCP layer analysis. What we are doing here is that if the packet has a TCP layer, we extract TCP specific information. The S port here is the source port, and the D port is the destination port. TCP flags are important because they control the connection state. Common flags include SYN for connection start, ACK for acknowledgement, FIN for connection close, and RST for reset. So scapy represents flags as strings like S for SYN, SA for SYN ACK, and PA for PSH ACK. And why are we checking for TCP specifically? Because not all IP packets are TCP. Some are UDP, ICMP, or other protocols. So we need to verify the layer exists before accessing its fields. So that's all for the TCP layer checking. Now let's move to the UDP layer part. And UDP is simpler than TCP because it has source and destination ports, but no flags or sequence numbers. Why? Because it is connectionless. So we are using elif because a packet can't be both TCP and UDP. It is one or the other. UDP is used by DNS, DHTTP, and many streaming protocols. Capturing UDP packets lets us see DNS queries, which reveal what domains a system is looking up. Now let's proceed to the ICMP layer analysis. ICMP is the Internet Control Message Protocol. It is used for ping, trace routes, and error messages. ICMP has types and codes. Type 8 is echo request, which is ping. Type 0 is echo reply. Type 3 is destination unreachable. Capturing ICMP lets you see network diagnostics and error conditions. Now let's proceed to the packet summary section here. Scapy's summary method gives a one-line description of the packet. It is incredibly useful because it shows the entire packet structure concisely. For example, an HTTP request might show what you're seeing on the screen, and this tells you that it is an Ethernet frame containing an IP packet to remote HTTP port with SYN flag. The separator line makes it easy to distinguish between packets visually. Now let's move to the HTTP specific callback function. This function here is more selective. It only processes packets that have both TCP and raw layers. The raw layer contains the actual data payload. So we are checking if the packet is using port 80, which is HTTP, and either the source or the destination port must be port 80. Then after that, we are decoding the payload as UTF-8 text, and this works because HTTP is text-based. We also look for keywords like HTTP, GET, or POST to confirm it is HTTP traffic. And you can see all of that here. And if you check here too, you can see that we are printing the first 200 characters of the payload. This shows HTTP headers and the start of the request or response. The try except block here handles cases where the payload is not valid UTF-8 or doesn't exist. Then we silently ignore these errors. Now let's move to the DNS specific callback function. And here we are creating a function called DNS packets callback. We are doing this because DNS packets have a DNS layer and a DNS QR layer for queries. So here we are checking for both to ensure it's a query and not just a response. The QName field you are seeing contains the domain being queried. It is in bytes, so we decode it to a string. This is incredibly useful for monitoring because you can see exactly what domains a system is looking up, and this reveals browsing activity and application behavior. Now let's look at the functions that start the sniffing. And that is what we are naming the sniff all packets here. This function here uses scapy sniff function, which is the main packet capture function. The PRN parameter you are seeing here specifies the callback function, and for every packet captured, scapy calls callback with that packet. The count parameter you are seeing determines how many packets to capture. 0 means infinite, that is keep capturing until interrupted. The store parameter here that is beside the count parameter is set to false, which means by default, scapy stores all captured packets in memory because long captures consumes lots of RAM. And setting store to false processes packets on the fly without keeping them. Then we can see that we wrapped everything inside the try except to catch the Control C, and that is why we are using the keyboard interrupt here, which means that when the user interrupts, we print a summary showing how many packets were captured. Now let's move to the section where we are sniffing HTTP. You can see the function here, which is sniff HTTP packets. And this uses scapy's BPF filter syntax. The filter parameter you're seeing there takes a string in Berkeley packet filter format, and that is what the BPF means. The TCP port 80 you are seeing means only capture TCP packets where either source or destination port is 80, and this is HTTP traffic. Scapy does this filtering at the kernel level, so it is very efficient because we don't waste time processing packets we don't care about. We are using the HTTP packet callback instead of the generic callback because we want HTTP specific analysis. Now let's move to the DNS sniffing function here. And because DNS typically uses UDP port 53, so our filter here is UDP port 53. And this captures DNS queries and responses. We use the DNS specific callback to extract and display domain names being queried. This is one of the most useful package sniffing techniques for security analysis. DNS queries reveal what services and websites a system is accessing. And next, we have the main function. And this is the function that ties everything together. And if you look at the function, you can see that first we check if the script is running as root. Then the getEUID function returns the effective user ID. 0 means root. So if no root, we print an error and exit. Package sniffing won't work without root privileges because it requires raw success access, and that is why we need the root privilege. We are also printing one in here about legal and ethical use because unauthorized packet sniffing is illegal in most jurisdictions. Now let's proceed to the menu loop, and here we are using the while true loop. Looking at this, we are resetting the packet count to 0 at the start of each loop iteration, and this gives accurate counts for each capture session. Looking at the menu, it offers 4 options. Option 1 to 3 call the respective sniffing functions, and option 4 exits. Also, if you look everything in the while true loop, you can notice that everything is clean, and each option is a single function call. All the complexity is encapsulated in the sniffing functions. We are not bringing all the complexities here, so you can see that this is quite neat. Now let's proceed to the entry point, which is where we have the if name equals main section. And what we are doing here is that we are importing our OS, you can see that here, because we only need it in this block for the root privilege check. So we are wrapping main in try except to handle interruptions and unexpected errors gracefully. Keyboard interrupt here catches the Ctrl+C at the program level in case the user interrupts between menu selections. And the generic exception catch here handles any other errors and displays them before exiting. So that's all for the code walkthrough. And before we go through the demo again, let me quickly explain the mechanisms behind package sniffing in the context of this tool we've just built. When you call scapy sniff function, here is what happens. Scapy puts your network interface into promiscuous mode. Normally, a network interface only accepts packets addressed to it. So in promiscuous mode, it accepts all packets on the network segment, even those addressed to other hosts. Scapy uses raw sockets to read packets directly from the network interface. Raw sockets bypass the normal TCP/IP stack and give you access to raw network frames. For each packet, Scapy parses the layers. It identifies Ethernet, IP, TCP, UDP, and application layers. It then builds a packet object with these layers accessible as attributes. Your callback function then receives this packet object and can inspect any layer or field. This is why you need root privileges because regular users can't create raw sockets or put interfaces in promiscuous mode. These are privileged operations. And I mentioned the BPF filters earlier, so let me explain it better now. The filter syntax we used, which is the Berkeley packet filter, was originally developed by TCP dump and adopted by many tools. Common BPF filters include the TCP port 80, which is for TCP packets on port 80, UDP port 53, which is for UDP packets on port 53, and we have others as you can see on the screen. And I must add that you can combine filters with and, or, and not. For example, you can use TCP port 80 or TCP port 443, and this will capture both HTTP and HTTPS. BPF filters are compiled to bytecode and executed in the kernel, and this makes them extremely efficient. Now, Scapy has different layers as well. It has the Ethernet layer, which is for MAC addresses and frame type. It has the IP layer for source and destination IP addresses. It also has the TCP layer for source and destination ports. That is also used for flags and sequence numbers. And lastly, it has raw layer, which is the actual HTTP data. Now that we know all of this, let's go ahead and rerun our code to see the demo again. So to rerun that, you need to save this, then come here and type this, which is sudo python sniffer.py. Then you rerun it and you input your password because we need the root privilege. And now you can see all the options again. So we can try it with the first one again to see what it looks like. And now it is sniffing all packets. So to stop it, we can use Ctrl C. You can wait for some seconds for it to start sniffing the packets. And now you can see that we have a couple of packets already sniffed. You can see packet 13 and it's going to continue like that. So this is how to build a simple packet sniffer using Python. And as our packet sniffer continues to run, I have a challenge question for you. And the question is, why does packet sniffing require root privileges? I repeat, why does packet sniffing require root privileges? I'll be waiting in the comment section to see your answers. That's all for this lesson. If you're yet to subscribe to our YouTube channel, please do that now. Also, do not forget to like, share, and comment. Thank you so much and see you in the next lesson.